Okay, so here we're going to work on, or we're going to introduce integration by parts. All right, so here, integration by parts. All right, so to now, really we're limited to our basic integration formulas like the power rule, right? And then some substitution as well, and then a few trig, a few trig integrals. And inverse trig, as we saw in an earlier section in this class here. So now we're going to take a look at something called integration by parts. And this all stems from really our product rule of differentiation. Right? It gives me an avenue that to integrate certain functions that have a particular form. Really, it's kind of a way to undo. You can think of it as almost undoing the product rule, right? And as we recall, so let's kind of run through steps in the formula here of the product rule first, and then how this is related to our integration by parts formula. All right, so now h prime of x, so remember product rule here, we get f prime of x, g of x, plus leave f of x alone, and then times g prime of x. All right, so that's our basic product rule here. So now from here, we're going to derive a formula that will allow me to integrate certain functions, right? Or certain product of functions. So I'll start here by, so we have this. Now what if I take the integral of both sides here? All right, with respect to x. Okay, so if I do that, right, remember the integral of a derivative is just the original function itself. So we go back to, this is h of x, but h of x is f of x dx. All right, so the integral here is just f of x times g of x. All right, and then here I'll simplify this, or I'll rewrite this in terms of two integrals, g of x dx plus the integral of f of x g prime of x dx. All right. And now from here, I'm going to rearrange a couple things here. I'm going to rewrite this. I'm going to solve for this quantity here, the integral of f of x g prime of x dx. Now, f and g are just general functions, so it really doesn't matter, right? They're interchangeable in how I think of them, right? I just chose this particular one. All right, so if I solve for this, then my formula becomes f of x g of x minus the integral of f prime of x g of x dx. Okay, and this is essentially my formula for integration by parts. Now, by convention, right, almost all calculus books I've seen do this, right? So we make a substitution to have a more compact version, right? We let u be the function f of x, and we let v be the function g of x. Now, using differentials, we know that the change of u is f prime of x times dx. The change in v, dv, is g prime of x dx. Okay, and again, these are just conventions, right? So it's a formula, so we can kind of plug and play with these, right? So that means that now this reduces to plugging stuff in. This is u dv, right? We see dv there, right? Just kind of matching things up. U dv equals to uv minus the integral of v du. All right, and here is our formula for integration by parts, right? And again, as long as f and g have continuous derivatives. Now, we won't really need to prove that here. We'll kind of assume, or we'll do a quick check, right, that they do have continuous derivatives, right? And at least in the interval that we're integrating, or we can assume that when we do integrate the interval, that the integral is valid where f and g have continuous derivatives. Okay, So here's my formula here, and again, integration by parts. Now, I'll start this video off, we're gonna do, or I'll end this video here with an example, okay? Now, I'm gonna show you two ways to do this example, right? One way is to use the formula, right? Now, whenever I teach this topic, I always do one with the formula, and I always have to kind of teach myself the formula because this is not how I actually do these integrals. So I'll show you the formula form, and then I'll show you a different approach that I use. This is how I was taught, and I found it to be more straightforward. So let's start here with an example. So the example is, I want to find the integral, evaluate the integral x sine of x dx. Okay, so here I want to essentially determine what's my u and what's my dv, right? So this is where I start, right? So it's given to me in this format. First of all, you try to find the integral. Is this a substitution integral, right? Is this a basic integral? And it's neither of those things. So then our new tool is this integration by parts. Right, so looking at this, I'm going to choose u to be x. And I'm going to choose dv to be this quantity here. So dv is sine of x dx. All right, and then taking the derivative, right, differentials du is 1 times dx. And then here integrating to find v is negative cosine of x. I'll save the plus c for the end when I'm done with my integral here for my final result. Okay, so just remember it's in the back of our head there that there should be a plus v there. All right, so now let's take a look here what comes next. Right, applying the formula, right? So the integral of x sine of x is uv, so here we get negative x cosine of x minus the integral. V is a negative, so negative and a negative, let's just get that out of the way, is plus cosine of x, and then du is just dx. All right, and now notice that we're not done integrating, right? There's still one more integral there, but it's a basic integral, right? So we get negative x cosine x plus sine of x, and then of course plus c there. And now we are done here. Okay, now as always, right, you could say, well, is this in fact the integral, right? You did this, but like, does this check out? All right, so again, as always, when working with integration, you can double check that by taking the derivative of the antiderivative, right, what you just found. So we'll do that once here just to see that this is a valid technique here. So we use the product rule here, so we get negative 1 times cosine of x plus x sine x. And then this becomes the derivative of cosine is plus cosine x, derivative of c is 0. Right? And then we see here that goes away, and we get x sine x. So that checks out, right? Great. All right? So we see kind of this undoing, right, of the product rule of differentiation. So one question you might be asking yourself is, well, does it matter my choice in u and dv? And yes, it is going to matter here, right? So let's say that I started this problem here. Again, I had the integral of x sine x dx, and I said, well, I want u to be sine of x. And that leaves dv to be equal to x dx. Right, so this is u, and this quantity here is my dv. All right, okay, and then that means that du is cosine of x dx, and then v is x squared over 2. Okay, now plugging into my formula, I see, okay, so we get x squared, so u times v, x squared over 2 sine of x, minus the integral of, what was it? V du. So v is x squared over 2, du is cosine x dx. Now here we see, oh, I actually have a even worse problem than when I started, right? At least in the first one, the x was just of the first power. Now I have an x squared and I still have a trig function, right? And I can continue going if I want by applying parts again, but we're really going to be stuck here in this kind of pattern that if we keep using the u to be my trig function, well, the dv being the power function, we're just going to keep increasing that power. So again, right, it's okay to try stuff, right? What you're going to find out is you just need to try a thing, see if it happens. All right. Here, stop if it looks more complicated, right? If your resulting integral is not basic and it looks even more complicated than what you started with, then just scrap it. Be like, all right, this is not it. All right, I need a different approach. Okay. So again, the choice of u and dv is important. All right. It will lead us to either a basic integral or something that can be more challenging. All right. Now, as I said, this is not how I usually use integration by parts. I always, u dv, that's always in my head, is kind of jumbled because I don't use it on a regular, right? If I used it regularly, then I'd be more, it'd be more common, more natural for me to use. But here's what I do, right? This is the way I was taught when I took this class, this calculus, second semester calculus. So alternate approach. So when I get an integral like this, x sine of x dx. Okay. So instead of thinking of u dv, I think of setting this table up. And I set 2 columns with d and an I. Right? The d starts for differentiate, and the I stands for integrate. And I split up this function, right? I want to take the derivative of one function, and I want to integrate the other one. Right? And again, right, it is going to matter the choice that I make here. Now, a guideline here is I want to take the derivative of a function where I know I will eventually get to 0. All right, if possible. Sometimes we'll see it won't be possible. We'll get to that in a second. All right, and then integrate the other function, right? And hopefully I can evaluate that integral. And one thing to keep in mind, right? Well, let me just work through this, right? So there are a couple things here that I'm going to do here, right? So once I pick my functions here, I'm going to go ahead and differentiate, right? And how long do I differentiate for? Until I get to 0. And we'll go over examples where what happens when I don't get to 0. So derivative of x is 1. Derivative of 1 is 0. All right, and then on the other end, I want to integrate. And here I just want to go until I get to the 0 row. So derivative of sine is negative cosine x. Derivative of negative cosine x is negative sine of x. All right, so now once I have this here, I'm going to alternate my signs, right? I'm going to start with positive, but then minus positive now. And also we need to just keep, at the end now, it just keeps down to keeping track of signs. This one will be positive, this is negative, this is positive. And I'm going to draw these arrows here. All right. And then here we get negative x cosine x. So I'm going to multiply. Right, and then negative is plus, so plus sine x. Now, the last one, when I kind of multiply over, I would normally integrate, right? That would be the third step, but here we get 0, so there's nothing to integrate, so the last thing is just add the plus c. Right? Okay, and now notice here, this is exactly the answer that I got before, right, using this approach. Now, the reason this works is because we're doing the u dv, right? We just masked it in different ways, right? Right, u dv. So when I integrate this dv, this is v, right? So that first multiplication is that uv, right? And then that last multiplication here is already the evaluated integral of v du. Okay, so it's really the same thing. All right, it's just in table form, and I'm left not worrying about what's u, what's dv, right? Instead of just, I'm gonna pick one to differentiate, one to integrate, right? That's it, right? And this is the approach that I take, right? I use this kind of table to help me out and guide me in trying to integrate by parts.